this is a curious, maybe even the only case of the expansion of both classical mechanics and quantum mechanics simultaneously. We've already seen how followers of Kozyrev have been able to derive, in a pretty simple way, for example, Heisenberg's uncertainty, right? So a theory like this might allow some funny stuff to happen, right?
Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert de Neyland, who has been the greatest living philosopher before me. This is yet another video from this series. Let's talk about some crazy Russian theories of a recent past. So today I want to talk about Nikolai Kozyrev and his theory of time and causality and what he calls the causal mechanics, alright? So I've been reading quite a lot of him a couple of years ago and made extensive notes, alright? Like, unfortunately, most of his texts are in Russian, but anyway, for some logistical reasons, let's put it this way, I've lost my notes. So this video is only gonna be like a very superficial, overview / introduction style video, because again, I'll have to read it all again to refresh my knowledge, but I mean, I remember some of it. And I've based my current video that you're going to watch just now on specifically only one of his works, although he has many, okay? He has been working on this theory for several decades. Anyway, let's begin.
All right, so we shall talk about the theory by this guy, Nikolai Alexandrovich Kozyrev, or you may look into his English page on Wiki. Let's talk about it a little bit. So these are his years when he was alive. I have to say that only about a quarter of his works are devoted to the topic we're going to be discussing here, which is so-called causal mechanics. But let me give you a brief sort of introduction to how he acquired these results, or more likely, how was he motivated to acquire these results in the first place? So again, only 1/4 of his works, about so, are devoted to this topic. But this is actually the most interesting, I would claim, quarter of his works. Like, otherwise, he was a pretty successful mainstream astronomer. Like, there's some crater on the moon named after him. There's an asteroid named after him, etc. So what you should know about him is that he spent some 10 years in various prisons and concentration camps in the Soviet Union, connected to the so-called Pulkovo affair, where many physicists, astronomers were, let's say, oppressed by the regime in the Soviet Union. I mean, people were having fun back then. And one of the things like he was thinking about, because he was working, in Siberia, like it was very cold there, etc., etc. So at some point, he actually asked himself a question, like, how did he survive, And he had this almost esoteric, you might call it, idea that there must be some hidden source of energy, that was basically kind of feeding him. So I'm only giving you this short biographical thing to highlight how actual motivation, plural, of our ideas are sometimes very different, to the way we present these ideas logically afterwards, like post hoc sort of way. So he started to think that maybe not only like people, roughly speaking, but also stars may have a different source of energy with respect to the usually acknowledged one, okay? And he got a Doctor of Science degree with this sort of work. Dealing with sources of energy in stars. And luckily, recently it was published in English, his doctoral thesis, which you might read. So it's this one. I will obviously link all of this in the description. It's very technical though, okay? Like you can see, it's mostly formulas here. But he arrives at pretty interesting results, which we shall only briefly discuss right now, okay? So this is what it says in abstract, actually, of his thesis, that stars are, according to Kozyrev, are machines directly generating radiation with basically no reactions taking place, Speaking of this fission/fusion type of narrative, well, according to Kozyrev, there aren't either fission or fusion, at least let's put it this way, they are not the main reactions that are producing the stellar emissions, okay? So stars only exist in conditions where classical laws, meaning laws of physics, are actually broken. And the way he arrives at this conclusion, this is a very like brief sort of idea-esque way of briefly communicating the idea of his thesis, okay? So if we look at the mass, radius, luminosity coordinates, then stellar emission in these coordinates represents some surface. We're speaking very abstractly here, right? And the production of energy represents another surface, at least theoretically, in these coordinates, okay? Like, if you want, I may do a complete breakdown of his thesis, but then again, it's gonna be very brief, just because it's very technical otherwise, okay? So all the stars theoretically should lie on the intersection of these surfaces, right? One which determines emission, another which determines production of the energy to be emitted, right? But they don't. That's kind of the problem he almost immediately encountered. So factually, stars only seem to lie on the surface which determines their emission. What does that mean? It means that production of energy is basically unknown, you know? Like, we don't really understand how it's produced, okay? As if there is actually no production at all. So it's kind of the point of Kozyrev that stars seem to be converting time, in quotation marks, into energy directly, okay? Now, connected to this, we shall look into it with respect to his causal mechanics a little bit later. But there is also a neutrino conundrum connected to that, because according to Kozyrev's theory, the temperature in the sun should be around 6 million Kelvin. According to some accounts, again, don't quote me on that, like some people have looked into it and have claimed that this is the temperature that corresponds to the observable neutrino counts from the sun. You may know that there is a so-called missing neutrino problem, where in modern astrophysics, specifically heliophysics, we assume that the temperature within the sun is more likely to be in the ballpark of 14 million K and not 6 or 7 as Kozyrev states. So in this case, you will have to have a bigger neutrino count, right? And this is why we have this missing neutrino problem, okay? But I have to add here that basically the summary of this is that if Kozyrev is correct, we'll observe exactly the amount of neutrino, at least according to some accounts, all right, that we do observe, all right? But in modern heliophysics, you observe less than the sun emits, so they have to fix it somehow. And they fix it with the neutrino oscillations, where we basically assume that neutrinos have mass and turn into one another, okay, along the way from the sun to our detector. But anyway, I have to add on top of it all that in principle, Kozyrev's theory does not contradict either nuclear fission or fusion taking place within stars. It's just that according to him, again, the production of energy happens irrespective of any reactions of this sort, okay? So reactions are only some secondary type of thing. And here I wanted to note, this is not what Kozyrev talks about, but anyway, like in humans, you know, we produce around 1 watt per kilogram of energy, like basically the human body emits around 100 watts, roughly speaking, which is if we take a mass of a human being as 100 kilos, I mean, roughly, the ballpark, okay, is such as roughly 1 watt per kilogram. Whereas for the stars, actually, it's much less. Like, if you look at how much the sun emits, it would be something like a tenth of a milliwatt, okay, per kilogram of mass of the star. And some people actually compared this to the energy emitted by decaying leaves. Like, it's very small, okay? It's just that the sun is huge, and it has so much kilos that even this very small emission of energy turns into a very big emission of energy, all right? But note here that we have a 10 to the minus 4 sort of difference in orders of magnitude here, okay? We'll encounter this number many times later. Again, I have to emphasize that Kozyrev did not talk about this, but long story short, stars don't emit a whole lot, okay? So maybe it's some sort of alternative process that is responsible for their emission, or rather production of energy in the first place, all right? And one other thing, I am, by the way, here mostly talking about, or at least we will be talking about, this document, which I'm gonna also link in the description. Now, as you can see, the text is searchable, so you can use like whatever translating device you want. If you want to kind of read it in English, for example, or any other language for that matter. So we're going to be talking about this little work from 1958, okay? Again, I've lost many of my notes. I only like vaguely remember some of the other things he talks about, so I'll pepper them in when necessary, let's put it this way. But in this document, he talks about atomic mechanics / quantum mechanics as being basically, we're already kind of coming to this causal mechanics. This was kind of the intro, like what made him think about those things. And this was specifically the mechanism of production of energy within stars, okay? So when he thought about it some more, he realized that it is the false identity between causes and effects which causes the quantum mechanical description of reality into the probability realm. So basically we are mixing causes and effects, taken philosophically, like logically, all right? And this forces us into the probability realm because, like, again, the determinism is lost because, again, we can't distinguish between causes and effects, which he claims we should be able to distinguish. And then the determinism would be restored, so to speak. And this has led him into the development of what he calls the causal mechanics, which is, again, this document is sort of like the manifesto of causal mechanics. And we're going to be talking about this. So again, it's 1958. So he was, 50 years old when he formulated this document specifically. And in another work, which I only vaguely quote here from 1963, he actually more precisely sort of defines what is the cause and what is the effect, and it can be defined logically, right? So if from A follows B, it means that A is the cause and B is the effect, all right? So in some sort of mechanical process, not all mechanical processes, by the way, have this causality. Like some of the mechanical processes are just identity, basically A equals B, right? Which is what, regular vanilla mainstream physics deals with. It's always A equals B. And he says that this is what brings descriptive character into the physics. So descriptive as opposed to explanatory, basically, right? And he says in order to bring explanatory character back into physics, we have to, again, distinguish between causes and effects. So it can be made logically as such, again, where A is sufficient for B, if you wish. More logical reading. So in this document that we talk about, he formulates 5, actually 6, but we'll delay the 6th one for a while, axioms. They can be found, let me just find where he starts talking about this. Well, basically here. Yeah. So this is axiom number 3, number 2, etc., etc. This is page number 9. So what are these axioms? Let's briefly talk about them. So axiom number 1 is that there is a fundamental difference. These are the axioms of causal mechanics, all right? So axiom number 1 is that there is a fundamental difference between causes and effects, and it is absolute, which means it is independent of the reference frame, right? And some of you might be disappointed or conflicted in this respect. You might say, well, don't we have like relativity theory, which says that the simultaneity, I guess, is relative, right? It depends on the reference frame, and therefore, in some reference frames, the causes would be reversed with respect to the effects, for example, right? And to which I might answer, I don't think Kozyrev actually made this point, that, for example, in thermodynamics, where we have this asymmetry between causes and effects, right? For example, entropy is rising according to the second law. So there is some sort of temporal asymmetry. So we still don't know how to work with this in relativity frame, right? Relativistic thermodynamics is non-existent, basically, even to this day. So, which means that relativity is not the be-all, end-all, as they say, okay? For example, we don't know what happens to temperature and entropy under relativistic transformations. It's just not developed, okay? Like, people have opinions, but there is no how shall we say it, agreed upon type of formulation of this sort, right? Relativistic thermodynamics. It's basically non-existent. So in this respect, Kozyrev might be in the right here, you know? Like if relativity contradicts him, it might actually be a sign that relativity is screwed in a way, and not Kozyrev's theory is screwed. But then again, it's all, how shall we say it? Disputable, let's put it this way, okay? Anyway, this is the first axiom, that there is a fundamental difference between causes and effects, and it does not depend on the reference frame. Now, axiom number 2 says that causes and effects are always spatially distinct. So it actually follows from the impenetrable character of Newtonian bodies, you know, basically solid balls, which means one ball is roughly in one point in space and another is in another, which kind of necessarily brings us to this point, that the distance between causes and effects might be arbitrarily small, but it is never equal to 0. Okay, so he uses delta, but I often, like in this document, I just put dx. So some non-zero interval between the cause and effect in spatial sense. All right, that's the axiom number 2. The axiom number 3 is that the causes and effects which are not spatially distinct. Now here we've agreed that they should be spatially distinct, but if they aren't, then they aren't really causes and effects, all right? It's just the same thing. And he gives the example of Newton's second law, where you have F equals ma. So he says that it is exactly the identity type of law, right? F equals ma, and it means that it's basically the same thing. It's not, F, if F then ma. It's more like F equals ma. So it's not a causal link, basically. Hopefully you can see the difference, right? It's not F, from F follows ma, but F is equal to ma. So it's not a causal link. Then point number 4 is that causes and effects are always temporally distinct. So with 2, we require that they're spatially distinct. And in 4, we require that they are temporally distinct. So there is always some non-zero time interval between the cause and effect. And again, we might depict it as delta t or dt if you wish, okay? And then the axiom number 5 is that time has a special absolute property, directionality, right? Time goes from past to the future, which makes them fundamentally distinct, right? This is exactly what we need in order to formulate some sort of causal link, right? Some sort of absolute causal link, because the time goes from causes towards effects, right? The time is directional. And this property is related to the difference, again, between causes and effects. So this is the quote from his document that we're discussing right now, that true mechanics must be causal, which means it must allow experimental distinction between causes and effects. Whereas otherwise, we're dealing with the same sort of objects that the regular Newtonian physics deals with. That is, we're going to be talking about material points and forces. By the way, like he actually makes this distinction that you can reformulate mechanics in terms of energies, for example, but then you would exactly lose this perspective. You would exactly lose the distinction between causes and effects. And he actually gives the example of where it has been done completely, like for example in quantum mechanics we're only dealing with energies, like the notion of force is absolutely absent in quantum mechanics, and this is, in his opinion, what leads to all these flaws that quantum mechanics demonstrates, right? So he says we need to look at the forces again in order to restore the causal links. We're going to be working with three-dimensional Euclidean space and one-dimensional anisotropic time. Now, what is anisotropic in this context? It means that the motion of time forward is fundamentally distinct from the motion of time backward, right? So the time has directionality to it. In this framework, any process, any causal process, I should have added, is a sequence, like a train of elementary causes and effects. All right. So any complex process is like this sequence. Whereas we might actually consider an elementary effect of, event of causality. And for this, we may introduce a velocity-like parameter, because per axioms 2 2, axiom 2 says that we have a interval between the cause and effect, even an elementary one, of dx, right? They are spatially distinct, and 4 requires that they are temporally distinct. So we might just take a ratio of dx to dt and thus get some velocity-like parameter, roughly speaking, meters divided by seconds, right? So we might construct this ratio. So in this document that I've shown, let me show it to you again, this one. Maybe I'll show it to you actually here. Like, for example, you see this C2 is the velocity that we get, right? Again, he uses the delta sign, not d as I do, but it doesn't really matter, does it? So C1 in this convention would be just speed of light, and C2 is this speed of causality, as we might call it, right? It would be determined as the ratio between the spatial interval between cause and effect divided by temporal interval between the cause and effect, right? So we might actually, I think sometimes he calls it the passing of time, right? And he says that this is the fundamental constant. Again, if we look at elementary causes and effects, right, divided by spatial interval dx and a temporal interval dt. So there is only space and time between the elementary cause and effect. There are no physical bodies between them. Thus, this C2 constant is the property of space and time itself and not of physical bodies. So here we need to do a sort of a mathematical, how shall we say it, pit stop, so to speak. So he spends quite a lot of time discussing the properties of these, of this value, basically. So you see, since the time is directional, so motion of time forward and backward are not identical, it means that dt is actually a pseudoscalar. So let me spend some time explaining what that means. So a scalar is just a number, right? But a pseudoscalar is a number which, let's just put it this way, it behaves differently when you add it and subtract it, right? Because the addition of time corresponds to motion forwards in time, but the, how shall we say it, the negation, like the minus dt, corresponds to motion backwards in time, and they are not identical, again, per axiom 5. Time is directional, right? Motion forward is not equivalent to the motion backward, okay? Whereas in regular physics, in pretty much any physical law, you will see that it's not the case, that dt is a scalar. But in this theory, in causal mechanics, it is a pseudoscalar. Now, if we divide a scalar by pseudoscalar, we get another pseudoscalar, right? So the motion, the passing of time forward and backward, they're different, basically. And it will be probably the easiest to explain this. I think I'll talk about this here. Let's just read what I have here. So C2, it's just one comment, right? It's not the macroscopic causal velocity, but it's the causal velocity in elementary act, right? Elementary connection of cause and effect. Again, we've kind of agreed that any actual process, macroscopic you might call it process, is the sequence of these elementary processes. So C2 corresponds to the elementary process. Like the real macroscopic causal velocity might be different from it. And you might think of it as an analogy, you know, where we have a velocity of gas which is not equal to the velocity of actual molecules, right? So in this sense, C2 is the velocity of molecules, whereas the velocity of the macroscopic causal process might be different from it. Like generally it would be smaller, right? But it could be bigger as well. Anyway, let's return to the discussion of what is a pseudoscalar. So it would be actually the easiest to demonstrate not with the pseudoscalars, but with pseudovectors. So let's try to do that. What is a pseudovector? Now, if you know anything about linear algebra or tensor analysis, I mean, it should be quite obvious to you what I'm going to say here, but I'm trying to explain this so that literally everyone would understand it, all right? So imagine we have a regular vector, like for example, regular velocity. So we might have a body here that moves up with the velocity v. Okay, so this is a regular vector. Velocity is a regular vector. It's not an axial vector or pseudo vector. This is how a regular vector would behave. Imagine I have a mirror here. So the mirror imaged object, how would it move? It would move the same, right? So the velocity vector under mirror image doesn't change. But if we have an axial vector, it would change. Because axial vector is not really a vector. It's actually an object of a higher dimension, so to speak. It's a tensor of rank 2 at the very least, okay? So let's try to construct an example of this sort. Like, what is the most, let's say, common axial vector that we might encounter? This would be angular velocity, okay? So angular velocity as an axial vector is determined as such. So if we rotate, I mean, it's conventional, so you might define it vice versa. But anyway, if we have a clockwise rotation, then this velocity vector, angular velocity, I should say, would be directed from us. So this is the common depiction of a vector pointing into the plane of picture, okay? This we call the axial vector of angular velocity. And if the stuff rotates counterclockwise, we would say that the angular velocity vector would be directed towards us, okay? It's like an arrow, right? Here we see the feathers because the arrow flies from us, and here we see the tip of the arrow, so it flies towards us. So let's take a look how this behaves in this mirror sort of reflection. We just saw that the regular vector, such as velocity, it doesn't change, right? Well, what if I have a bottle here and a cap, okay? So if I turn it like this, the cap, it would go downwards, right? It would be screwing onto the bottle. This is how you close the bottle. So you might say it's the angular velocity vector corresponds to the motion of a cap on a bottle, okay? But the mirror imaged cap, how would it behave? It should behave the same way, right? It would rotate like this. But if you rotate the cap on a bottle like this, it should unscrew, right? So as you can see, the axial vector, angular velocity of the cap in this case, it reversed, right? The cap should move the opposite direction. So this is, I'm trying to illustrate, okay, the difference between a scalar and a pseudoscalar, though I'm using vectors for this. So regular vectors, such as velocity, under mirror image doesn't change, whereas the axial vector change onto the opposite one, okay? Hopefully you get this example, but now we have to get back to scalars, right? These were vectors, but they behave in a very similar manner. So what does that mean is essentially that the motion of time, the very directionality, the fact that time can be represented as a pseudoscalar, it means that it should correspond to some sort of rotation, all right, in a perpendicular plane, okay? Just like we saw with the rotating cap on a bottle. Like if we assume that the motion of the cap corresponds to the motion of time, then something should be rotating around it, all right? Like, hopefully this makes some sense for you, all right? Anyway, so one interesting conclusion from this is that the mirror imaged world would be identical to our world moving back in time, just like we saw with caps moving up or down on the bottle, right? So yeah, I mean, obviously in this, in this case, the reflected cap would also go downwards, right? But it would be kind of broken, like this is not how caps behave in real world. So the mirror imaged world is different from our world by the same token, right? So we can say it's actually identical to our world moving backwards in time. Then we can talk about like the CPT symmetries in physics, but I actually don't want to do that. Like I feel like this video is becoming way too long in the first place. So yeah, so this is again the quote from the document is that the passage of time is essentially equivalent because it is directional, because the time itself is a pseudoscalar, it is equivalent to rotation of cause around the effect and vice versa, right? So I think it's a pretty big idea. And I've had this, idea, again, of trying to build mechanics starting from rotational motion. Again, the very fact of the asymmetry of time, the fact that time moving forward and backward are somehow fundamentally different, because again, we have the irreversible processes, for example, in thermodynamics, right? The entropy rising and stuff like this. It means that the rotational motion is actually more fundamental than the linear motion, because rotational motion is described by pseudovector. Again, just like the motion of time is represented by a pseudoscalar. But again, it's still pending, okay? I'm still thinking about this. So in an elementary causal link, there might be additional forces present. This is one of the interesting conclusions from causal mechanics. They would be linked via Newton's third law, the law of action and reaction, if you wish, which states that they should be equal in value in opposite in direction, but they might not necessarily be collinear, which would make a non-zero torque. Okay, so the system, because of this difference between causes and effects, might actually start rotating. So according to Kozyrev, the momentum is conserved, but the angular momentum is not necessarily conserved. So here would be a illustration of this. I took it from one of the presentations about Kozyrev. So in classical mechanics, we have this is cause and this is effect. So the Newton's third law makes them sort of equivalent. That's why, again, we formulate Newtonian mechanics as equivalence, right? F equals ma, not F from F follows ma. Whereas in causal mechanics, there might be these additional forces. So this K on effect, K acting on the effect, and K acting on the cause. Again, according to third law of Newton, they should be equal and opposite to each other. But as you can see here, they are not collinear, because this force acts over this line and this force acts over this line. So they would represent the pair of forces, so-called. So there would be a torque on this system, right? And the resulting forces would also be off-center, so to speak. And here, in a strict vector calculus type of way, you may represent it like this. Even though, again, I have to stress, this is not Kozyrev writing this, it's some of his followers. So yeah, and the additional force, we might say, again, I'm kind of doubting this a little bit, but this is what he has in this document, that this additional force, due to causal distinction between cause and effect, might be proportional to the initial force, like the normal Newtonian force, multiplied by the linear velocity of relative rotations of cause and the effect. This is the u. Divided by, because again, we need newtons, right? So we have to divide by some other velocity, and we only have one specific velocity, which is this c2 constant, essentially, right? Which represents the passing of time itself, the rotation of elementary cause around the elementary effect, or vice versa, okay? So yeah, and we'll talk about measurements some time later. Right now, we might say that the original force slightly turns. That's probably another way of looking at this situation. So we've had the initial Newtonian forces and they turned a little bit, right? So this produces torque now on the system. The difference in direction of additional cause and effect forces allows to make a distinction between them, because again, even in vector calculus, they're directed differently, right? The force on the cause is directed up and the force on the effect is directed down. So this allows us to construct sort of experiments where we can distinguish between the causes and effects according to Kozyrev. And since 1951, he did many experiments with gyroscopes. Again, why are gyroscopes important? Well, because you saw that, right? The rotating system has the pseudo vector describing it, and therefore all of these causal things would be evident in it, all right? Or pendulums, for example. So what he found, and I have to make a general comment here, like the experiments he did are a bit doubtful. And there is still no, let's say, general understanding whether he was even right with these experiments, because the scale of these effects, as we shall see later, is about this. So it's about like the additional forces would be like 10,000 times weaker than the regular Newtonian forces. Okay, so you have to make a pretty precise experiment to even determine them in the first place, right? And many people doubt to this day that the experiments of Kozyrev were legit. Okay, so I just have to tell you that. Obviously, here in this, for the sake of this video, let's just put it this way: we are considering Kozyrev as legit, okay? But many people would disagree with it. In fact, I have my doubts still as well. Like, this looks suspicious at the very least. But if we take it at face value, all of this is correct, all right? We'll just proceed as if it was, okay? So, for example, he weighed, I guess, the gyroscopes, and has found that the direction of their rotation does not change. It has no impact on their weight, basically. However, if we break the symmetry, so we introduce some sort of causality along the axis, like for example, if we introduce some sort of vibration or electric current or heat flow along the axis, we observe, again, this is if we are to believe Kozyrev, additional forces. We have to observe these additional forces if there is this sort of symmetry breaking, which again would turn our regular vector into an axial vector, roughly speaking. Don't think about it too much. Okay, and these additional forces would be directed along the axis, and they would be proportional to the linear velocity of rotation, just like our formula shows here, right? This is the rotation of cause around the effect, or vice versa. So this allows us to measure, again, we believe Kozyrev that he did measure it properly. We can measure C2, because if we measure the additional forces, like for example, the reduction of weight of a gyroscope, and we measure the normal forces, so to speak, the normal Newtonian ones, and we measure the velocity of rotation, from this expression, like we measure df, we measure f, and we measure u, we can find the C2 parameter, right? This fundamental constant according to Kozyrev of passage of time, or the elementary causality velocity, okay? So he measures this, again, if we are to believe him, as roughly this value, 2,200 kilometers per second. And what he notices is that it's almost exactly equal to alpha, the fine structure constant, multiplied by the velocity of light. This is true. Like, it's easy to see. So according to him, alpha itself, the fine structure constant, is simply a relation of these two velocities. The velocity of causality divided by the velocity of light, okay? And this connection, again, this is not something Kozyrev himself did. It was his followers that uncovered this interesting link, the link to Heisenberg's uncertainty specifically. Again, I have to note that in vanilla quantum mechanics, it's basically a postulate, the uncertainty. So let me show you how it's done. So again, this is not Kozyrev. You won't find it in his works, but some of his followers have found this link. Like, for example, our velocity of causality, C2, is alpha times c, which is the speed of light. And alpha is this structure, right? E squared divided by Planck's constant times the speed of light. It's in CGS units, right? The centimeter gram second, or Gaussian units, if you wish. So in this sense, we just put alpha here like this, right? So then c cancels, and we arrive at this. So this is our velocity of causality according to Kozyrev. And the Coulomb force would be just elementary charge squared divided by this elementary spatial interval between the cause and effect. Again, in CGS units, there would be no other constants here, right? So we take the square of charge divided by the square of distance. Then, if we multiply this by these intervals of space and time, roughly speaking, then 1 dx cancels out over here. Then we put dt downwards, and we notice that our dx over dt is basically C2 in the first place, right? And here we just derived that C2 is equal to E squared over h bar, right? The Planck's constant. And then E squared, the charge squared, cancels out, and we find that F times dx times dt is equal to Planck's constant, the reduced one, right? So this is basically the uncertainty relation, because what is F dt? It is the momentum, right? The momentum change. Whereas F times dx is the energy change. So you recover both uncertainty relations from this. Now, the factor of 2 appears out of statistics, right? If we assume the basically Gaussian distribution of momenta and coordinates, you get this characteristic square root of 2, which turns into 2 when you multiply them, all right? So here we've looked at the elementary thing, and here we look at statistical thing, right, with the Gaussian distribution. So you recover from this notion of Kozyrev, you recover Heisenberg's uncertainty, which is pretty big, if you ask me, okay? It arises naturally from causal mechanics, which is kind of big, again. So yeah. I have to note that in this interpretation, particles still do have positions and trajectories, which makes it close to Bohmian mechanics, right? I'll remind you that I have a video about it, which you might watch if you wish. I'll also remind you the stupid debunking, in air quotes, that Sabine Hossenfelder did, which I mentioned in this video. But recently, there was apparently an experiment which rules out Bohmian mechanics. But then again, it doesn't, okay? Long story short, I'll link this paper. It's not even a paper, it's more like an article, which debunks this debunking, okay? So once again, Sabine is wrong. I'm sorry. She is already twice wrong with respect to, she doesn't do Bohmian mechanics justice, let's put it this way. I also have to note that in Bohr's framework, you know, the postulates of Bohr of how atoms behave, this velocity corresponds to the velocity of electron at the first orbit, okay? Which is also kind of curious because it corresponds to the velocity of causality. But then again, like, it's something worth thinking about, but I don't want to stop on this and dwell on it for too much. Again, he proceeds, Kozyrev that is, to apply this thinking to planets. So he shows that the very fact that planets are rotating must make them asymmetric with respect to this speed of causality. Okay, so for example, if we're looking at Earth, so we're rotating like this, and it would sort of impact north and south hemispheres differently. So the conclusion, I'm not going to show you how you arrive at this conclusion, like again, I don't want to spend too much time on it, is that the planets must have a cardioidal shape, okay? A cardioid, so basically like, it would be like a heart shaped with like a, you know, the thing at the top, okay? And apparently, according to Kozyrev, this is exactly what the measurements, the gravimetric measurements of Earth show. Again, he spends quite a bit of time discussing this. I just don't want to dwell on it for too much. But according to him, this what explains like why do we have these continents in the north, right? Because that's where you would have this sort of thicker thing of the cardioid, and you have the Antarctica at the very south because it's sort of more oblong in the south, okay? Then again, in his vibration experiments, let me actually show to you how they were done. So this is what we have. We have the basically like a balance where we have a rotating gyroscope on one side, so its axis is vertical, and here we have a counterweight. And we introduce vibrations like this, again, to break the symmetry along the axis of the gyroscope. So what he got is that if you spin the gyroscope counterclockwise when looked from the top, its weight actually reduces, all right? But again, we need this vibration in order to introduce some sort of symmetry breaking along the axis. You can also do this sort of experiment. Here we have a gyroscope on like a pendulum, the axis should be horizontal in this respect, and we introduce the vibrations like this. And what you see is that your gyroscope, again, if we are to believe Kozyrev, it is deviated from the vertical, okay? So according to him, this allows us to see these additional forces in a vertical and in the horizontal plane, okay? So the sort of a cumulative effect should be like a three-dimensional force directed somewhere, right? But we can read out the vertical and horizontal components from these types of experiments, which again, according to his thinking, would lead us to distinguishing between the causes and effects. And the effect he got is, again, this sort of magnitude, okay? So, for example, the weight of the gyroscope would be reduced by roughly 0.01% or 10 to the minus fourth, right? Roughly speaking, 10,000 times with respect to the weight of the gyroscope itself. But it only is active when the gyroscope, again, rotates counterclockwise, looked from the top. I mean, obviously, we're talking about the experiments in the northern hemisphere, whereas the clockwise rotation did not reduce weight. Okay, and I have to make a mention of this Japanese experiment. So you see, there was a paper in 1989 which did exactly that. They've mentioned the difference between the gyroscope, the weight difference of the gyroscopes rotating clockwise and counterclockwise, and they found a significant difference. So, but the problem is, with respect to Kozyrev's theory, is that it's actually the effect is the reverse. So according to Kozyrev, the left rotation should reduce weight, whereas the right rotation, or clockwise rotation, shouldn't. But this paper actually, if you wish, it experimentally falsifies Kozyrev's thinking, because the effect should be the reverse. So I still don't know what to think about this. Well, first of all, according to regular mechanics, you shouldn't see any difference whatsoever, and they found it, okay? There is a difference, which is curious. But according to Kozyrev, it should be the reverse, right? So the left rotation should reduce weight, and the right rotation shouldn't. But here, an experimental paper again showing that it isn't the case. So a very strange occurrence. Like, I don't know what to make out of it. But yeah, there you go. So apparently this directly falsifies Kozyrev's theory. But still, the effect shouldn't be there if there was no difference, right? So it's very weird, I'm telling you. And in this paper, they also had the vibrations in there, like, how do you call it? I don't know the proper term, so let's just forget about it. Yeah, and in pendulums, we've already discussed this. So yeah, and we've already discussed this as well. So what he also says is that sometimes these forces, these additional forces of roughly 10 to the minus 4 or minus 5, as in case of pendulums, with respect to the general force, like a gravitation, for example, they seem to demonstrate some seasonal dependence. Like, I don't know, and this made me immediately think about the Shnoll effect. Like, if you don't know what Shnoll effect is, I will reference this presentation of mine from 2019. I'll link all of this in the description. And this leads him to formulate this sixth axiom. Again, I've promised that we actually have 6, right? But we'll leave one at the end. So this is it. He also stated that time has some other variable property. Again, why is it variable? Because he needed some explanation of apparent seasonal dependence of this effect. Oh, and by the way, I didn't mention this, I should have. So, regarding planets, right, his derivation, you might see it in the document itself. Like, he does quite a bit here. As you can see, there are some formulas. So, according to his thinking, the additional forces must become 0 at some latitude. And he finds that it is roughly 73 degrees latitude. And again, if we are to believe him, this is what is actually observed. Okay. So yeah. So they basically change sign, right? So to the south of this latitude, you have one sign of the force, and to the north, another. And this is what leads to this cardioidal sort of shape. Again, some people have debunked, in quotation marks at the very least, because this asymmetry of planets, because it should be observed actually with other planets as well, and it should be even bigger if they rotate faster. So he has a table over here. So for Earth, it should be this size of the effect, so to speak, this ratio of the velocities. And for example, for Jupiter, it would be, as you can see, well, at least an order of magnitude bigger, and so is for Saturn. However, people supposedly measured the shapes of Saturn and Jupiter and haven't found anything like this. So take it with a grain of salt, okay? Anyways, yeah, so we have to introduce an additional property of time, namely density. And it's not very strictly introduced, so it's kind of like a hand-waving argument that this passage of time seems to be faster or slower at certain points in time, right? Anyway, so yeah, and it seemed to be actually influenced by various processes in the environment. Again, seemed to be, if we are to believe Kozyrev. Like, for example, he did many experiments with these asymmetric rotational balances. I'm going to show it to you. Of this sort, where you have like a counterweight and a very long needle on a very fine thread hanging, right? So if there was some sort of irreversible process happening, like for example, how do you say it? Oh my god, dissolving sugar, for example, in water. That's an irreversible process, which is characterized by increase in entropy. Like, this thing would react to it somehow, as if this process was emitting something which was picked up by this. Again, irreversible processes, they are causal, right? They distinguish between the past and the future. Therefore, some sort of influence of this sort might be observed. Again, according to Kozyrev, it is observed. Like, I don't know what to tell you about this. Again, take it with a grain of salt. Or you can make experiments with balanced bridges, right? Like the regular electronics as they do. But if you put this resistor, one of the four, like far from the circuit, and you make some process near this resistor, again, according to Kozyrev, it becomes unbalanced. So something is happening here, okay? And one thing he did, which was kind of big, was he took this system, this balanced bridge with one resistor sort of removed far away, and he was looking at various stars and planets and like nebulae or galaxies, where he would take a telescope and close the aperture, close the how do you call it? The input from the telescope, basically, with some like a cardboard or something. So the actual photons would be blocked, right? And he still put this resistor as a receiver of the blocked light, so to speak. And apparently something happened as well. So his conclusion from this, like the resistance changed. His conclusion from this was that there is some sort of physical emanation of time, roughly speaking, happening from these stars, for example, right? Because again, the burning of stars is also an irreversible process. It increases entropy, right? So some, roughly speaking, rays of time itself, according to Kozyrev, I keep repeating, are emitted during that, okay? And even more so, this is what we just discussed. He actually found that this effect, the resistance of the resistor, I guess, changing, happens in 3 different points. So I'll try to illustrate this again. So imagine this is us looking at the sky, okay? We're pointing our telescope somewhere. So we have a visible position of the star, okay? So if I point my telescope onto this, my resistor reacts to this. And again, I repeat, we block, or at least apparently block, the actual emission. So it's not the heating of the resistor, it's something else, right? At least according to Kozyrev, okay? So the apparent position of the star. But what is the apparent position of the star? It's where the star has been when it emitted light, right? That we see right now. It might have happened like 100 years ago, for example, right? If it's 100 light years from us to the star. But we observe some change. What was really interesting is that he found that if you point your telescope at the immediate position of the star, where we don't see any star yet, but it took, if it's 100 light years from us to the star, like in 100 light years, it would be here. And if I point the telescope here, I also see the effect. So it's almost like an instantaneous emission of this, roughly speaking, time happens. But what was even more curious is that if I point a telescope, like this is the imaginary position of the star, right, where we see the light from it. This is kind of the real, where it is right now, but we don't see it there. Still, if I point my telescope there, according to Kozyrev, the same signal is received as well. So it's almost like it's instantaneous. But if I point the telescope to the point where the star would be when light, or let's say signal from Earth reaches it, which again would be removed, right? You also get the same signal. So you get the signal from the imaginary position where the star has been when it emitted light. You get the same signal from the real position of the star where we don't see it yet. And even in the future position of the star, you get the same signal, which is kind of crazy if you think about it, all right? So yeah, take of it whatever you like. Like, people still are trying to wrap their heads around it. And again, I urge you to take all of it with a grain of salt. But this looks kind of legit. Like, I've heard that some people have tried to debunk this, but they couldn't because this is actually correct. But like, it's all, doubtful, okay? So be careful with this stuff. But it seems legit to me. This will be my opinion. But it's just an opinion, okay? So, yeah. And he also found, again, if we are to believe him, that this emission of time that irreversible processes do, let's put it this way, according to him, it falls off linearly with distance. Like when he made these experiments with dissolving sugar, or for example, the evaporation of something, I don't remember what it was, acetone or something like that. Like, or if you take a foil and crush it, and it would start kind of unfolding a little bit. This is also sort of an irreversible process. It also, according to Kozyrev, emits some stuff like this. According to him, these emissions, again, they can penetrate some solid bodies. Again, if we close our telescope, for example, with a cardboard or something like this, it can still pass through, but not by much. Perhaps it could be, this is my sort of comment, it could be roughly equated to something between the beta and gamma radiation penetrative ability, right? Something like that. So with a layer of, I don't know, lead of 10 centimeters, you can pretty much block it. Or maybe not 10, you get the idea, okay? But it also, according to Kozyrev, this emission, this new sort of mysterious emission, can also be reflected by mirrors, specifically aluminum mirrors. Again, we use the telescope, right? The mirror telescope, the reflector, and it uses mirrors. So yeah. So according to Kozyrev, aluminum mirrors, at least aluminum mirrors, right, can reflect this emission just optically. But with respect to optics, it actually behaves differently. It falls linearly with distance, not as a square of distance. That would be kind of the difference. And we're moving pretty much towards the conclusions here. So there are certain myths about Kozyrev, like for example, maybe you've heard about it, the Kozyrev's mirrors, which have nothing to do with Kozyrev. It was Kaznachev who developed them. He just kind of called them Kozyrev's mirrors because, again, they are aluminum mirrors, supposedly kind of redirecting emission from a human body towards itself, sort of. But again, it has nothing to do with Kozyrev himself. He never developed anything like this. So you shouldn't confuse this with his research, okay? Some people claim that he worked on a time machine. Long story short, he didn't, okay? So in all of these things, like we're in a woo realm, so to speak, okay? So you have to be careful. Then some anecdotal stuff that I've read and listened to people talking about with respect to Kozyrev. Like, there is a guy who is developing a theory of electron based on causal mechanics, and apparently he has some success with this, but again, it's not the topic of this video to consider anything of this sort. Then anecdotally, I've heard that some people did hydrodynamic calculations taking into account, in the atmosphere of Earth that is, taking into account these additional causal forces of Kozyrev, and they've got some really interesting results apparently, but then again, it's all anecdotal stuff. Then I don't even want to talk about this right now, and these three images of a star, according to some people, again, would correlate to something like a Coulomb component, which is like in Maxwell's equations, for example, right? What is a Coulomb component? It's the immediate one, right? So it's the component which is emitted by this, the immediate position of the star, which we don't even see, right? Whereas the two others would correspond to advanced and retarded wave of Maxwell's equations, which kind of leads us to thinking about the universe in a Descartes-like way, right? Where we have the ether sort of connection between the objects and instantaneous like interactions between them. But anyway, if we're talking about this, I have to point out that non-locality, right, the immediate spreading of the signal would actually sort of make the causal mechanics self-destruct, because in a non-local universe, you can't disentangle causes and effects. Everything happens instantaneously. So, I mean, this is a thing to think about, but I don't want to dwell on it too much once again. So, yeah. So this is just me reading and commenting. So active forces, these are these causal forces, and passive forces, the regular Newtonian ones, can be actually, according to Kozyrev, distinguished by a physical experiment. At least that's what he tried to do. Okay, so in this respect, he was a, legit scientist. Like he tried to experimentally distinguish. And if it's not possible, we're not really doing science, right? If we follow the empirical method of Francis Bacon. So we can probably be able to construct a device. If we can't, then it means causal mechanics is incorrect. And this is also an interesting thing that he mentioned, that the equilibrium states are determined by minimal energy. So that means that any non-equilibrium state would be equivalent to a state of higher energy, and thus causal forces corresponding to passage of time might allow to build an engine generating energy from time itself, just like, in his opinion, stars actually work, right? They we're kind of returning to this point, right? That stars actually don't generate a whole lot of energy, and this is very, very in the ballpark of his 10 to the minus 4 additional causal forces, right? Yeah. Like, for example, on page 21, he gives an actual example of how you can build a sort of this perpetual motion machine based on causal forces. The problem is, I'm going to show it to you, page 21. This, like he describes it here, like one possible realization of a perpetual motion machine based on, again, the transformation of passage of time itself into the energy. The problem is that it only generates roughly 2 ergs per second, right? An erg is a 10 to the minus 7 of joule. So this whole machine would only generate about 100 nanowatts of energy, but of power rather. But this is the same order of power that 1 gram of solar matter produces, right? So again, we're in the same ballpark. It doesn't seem that insane if you consider this fact, right? It does look like stars might be powered by some, let's say, mysterious effect of this sort, right? But Kozyrev himself says that one needs to build a causal electrodynamics to describe that properly, like how stars might work in this sense. And he notes that, for example, the magnetic field is also a pseudo-vector, again, we're kind of returning to this point about rotations. So it corresponds to some rotation, just like time is a pseudoscalar in causal mechanics, right? So the reverse process is also possible, according to Kozyrev, where non-equilibrium systems might also decrease their energy and thus generate this emission of time, roughly speaking, right? Anyway, these are conclusions. So there is, again, like we've already seen, that according to Kozyrev, conservation of energy is not required by his theory. But I have a slight problem with it. You see, the thing is, Kozyrev's theory has anisotropic time, right? Time has a directionality, but it doesn't say that time is inhomogeneous. And conservation of energy actually relates to the homogeneity of time, right? So anisotropic character of time does not necessarily mean inhomogeneous character of time. So I have a bit of a problem with this, right? If you want to build actually a parameter that is, let's say, broken by directionality of time, it would probably be entropy and not energy. Again, this is a bit of a debatable topic, but this is what I would think about it, right? But anyway, the causal mechanics of Kozyrev, I think, provides some interesting philosophical or metaphysical, if you wish, tickling to the brain, right? Just as I said, like, what's the goal of philosophy? Turning obvious things into non-obvious things, right? And again, like, if we problematize mechanics to begin with by saying that, well, past is clearly different from future, you arrive at some theory that looks like this, that looks like what the causal mechanics of Kozyrev looks like, okay? And I have to add here that Kozyrev's theory cannot be wrong, principally. At least with respect to Newtonian mechanics, though it might be superfluous with respect to it. For example, he assumes additional properties of time, right? The directionality, maybe even, roughly speaking, the ability to be emitted and absorbed, right? But if these additional effects are not there, you just recover the usual Newtonian mechanics from it, right? Just like correspondence principle requires. Like, for example, if you take the infinite velocity of causality, like if the cause and effect are spatially distinct, so dx is non-equal to 0, but dt is equal to 0, that leads to infinite C2, right? Which is the ratio of these two things. And it gives you regular Newtonian mechanics, because with infinite C2, in the denominator here, everything turns to 0, right? And additional forces disappear, and you just recover regular Newtonian mechanics from it. By the same token, if you postulate C2 equals 0, where you have basically no causal links at all, you recover quantum mechanics, interestingly, right? So yeah, this is a curious, maybe even the only case of the expansion of both classical mechanics and quantum mechanics simultaneously. We've already seen how followers of Kozyrev have been able to derive, in a pretty simple way, for example, Heisenberg's uncertainty, right? So a theory like this might allow some funny stuff to happen, right? Again, sadly, I have to underline that not a lot of his works are in English, but if you want to read more, again, I'll have this link, then you can just go into this website, which is a collection of his works, and like, as you can see, there's plenty of papers here, plenty of articles, which again, all of them have searchable text, so you can just translate it with some sort of machine translator. Interesting, very interesting insight that time might actually be a pseudoscalar, right? So again, I'm returning to my own comment that time might be homogeneous, but it certainly isn't isotropic, right? Like, what does that mean? It's actually a question, right? I still don't really know what does that mean. But I guess, again, you can recover things like second law of thermodynamics from it, right? And the underlying importance of rotational motion to begin with, again. That's pretty big, let's put it this way. Mechanics, according to Kozyrev, may not be invariant with respect to time inversion and mirror reflection, just like rotational motion isn't, right? And as I've said, I've read it somewhere in his works, that if you make the time go backwards, you have to also mirror image the coordinates. So if the time would go backwards in our world, it would correspond to a mirror imaged world. And vice versa, in a mirror imaged world, the time would go backwards, okay, necessarily. Well, there you go. This is the causal mechanic of Kozyrev. Again, a very interesting approach to physics with apparently some measurable consequences, but I still have to put an asterisk here, is that many groups have tried to replicate this. Again, this Japanese group has replicated it, but you know, completely the opposite sign. So I don't know what to make of it. So yeah, but Kozyrev himself always emphasized that if it's not experimentally measurable, you can just discard the theory completely, right? In this sense, he was very scientifically oriented, okay? Well, that will be all, probably.
Thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.